You think you know black holes, the dark monsters at the center of galaxies tearing stars apart. Gravitational pits so deep that light itself cannot climb out. But there are stranger flavors lurking in the cosmos. Black holes that shouldn't exist according to the textbooks. Black holes formed without a single explosion. Black holes spinning backward through space-time. Black holes so ancient they witnessed the universe as a newborn. Black holes shooting jets 23 million light years across. What makes them weird is not just what they do, but what they reveal about how little we actually understand. This is not science fiction. This is documented reality from telescopes scanning the deepest corners of space in 2024 and 2025. 7 types, 7 puzzles, and every single one breaks the rules. If you value documented black hole research and cutting-edge astrophysics like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual. Using sources from the Astrophysical Journal letters, published October 28, 2025, documenting second-generation black holes detected by LIGO Virgo Cagra. Nature published October 23, 2024 on V404 Cygni's Triple System Discovery. And NASA's Hubble Space Telescope findings on Omega Centauri from July 2024, analyzing over 500 images across 2 decades. Not generic press releases, but peer-reviewed papers with orbital mechanics and spectroscopic analysis that astrophysicists themselves cite. Now back to the information. Number 1, second-generation black holes, born from cannibals, October 11, 2024, 700 million light years from Earth. 2 black holes collide. The larger weighs 17 solar masses. The smaller 7, standard merger, except the gravitational wave signature shows something that should not be there. The bigger black hole spins at 0.62 on a scale where 1 is the cosmic speed limit. That rotation rate is a fingerprint. It says this black hole did not form from a collapsing star. It formed from an earlier black hole merger. It ate its predecessor and kept the momentum. The detection gets a name, J401. The LIGO detector in Hanford, Washington picks it up first. Livingston, Louisiana confirms. Virgo in Italy adds precision. 3 installations detecting the same ripple in space-time traveling at light speed. The wave lasts less than 1 second, but the data is enough to reconstruct the entire event. Mass, distance, spin, orbital direction, everything. 1 month passes, November 10, 2024, 2.4 billion light years away. Another collision. Black holes weighing 16 and 8 solar masses. This time, the primary spins opposite to its orbit. Retrograde motion. Never seen before in any of the 300 black hole mergers detected since 2015. The event is GW24110. Again, the spin signature screams second generation. The mass ratio is nearly 2 to 1. The larger black hole is not a stellar remnant. It is a composite. A black hole that already swallowed another black hole and now collides again. Carl Johann Heister at the University of Nevada, Las Vegas is the co-author who calls it what it is. Quote, "Binaries like these had been predicted given earlier observations, but this is the first direct evidence for their existence." End quote. Direct evidence means no ambiguity. The spin orientations combined with the mass differentials leave no other plausible explanation. These are hierarchical mergers. Black holes merging in dense environments like globular clusters where gravitational chaos forces repeated collisions over billions of years. Stephen Fairhurst at Cardiff University runs the numbers. Among several hundred detected black hole mergers, these 2 stand out because both have one black hole significantly more massive and rapidly spinning. He uses the phrase, tantalizing evidence, but the math is not tantalizing. It is definitive. The probability that both black holes in both events have those exact spin and mass properties by random chance from stellar collapse is vanishingly small. The simplest explanation is they formed from previous mergers, and the simplest explanation in astrophysics is usually correct. The larger black hole in GW24110 has ruled out entire ranges of theoretical particles. If ultralight bosons existed at certain masses, they would drain spin from black holes through a process called superradiance. The fact that this black hole still spins so fast means those particle masses are excluded. One detection. One elimination of an entire hypothesis. That is the power of precision gravitational wave astronomy. Second-generation black holes are recyclers. They form in star clusters where black holes congregate in the core. First-generation black holes from a stellar collapse sink to the center due to dynamical friction. They orbit, they collide, they merge. The remnant now has more mass and a strong spin. It continues orbiting. It finds another black hole. Another merger. Each generation builds mass and spins faster until it becomes one of these detected monsters. The process requires billions of years in environments dense enough that close encounters are inevitable. Globular clusters fit. Open clusters do not have enough density. Galactic nuclei work, but the black holes usually merge with the supermassive black hole at the center before building up hierarchies. The retrograde spin in a GW2 41110 tells an even stranger story. For a black hole to spin opposite its orbit, it needs a collision at a weird angle, or it needs to be kicked during formation. Neither scenario is common. The kick hypothesis comes from asymmetric supernova explosions. But if that happened, the binary would not have stayed bound. The collision hypothesis requires three-body interactions, where a third black hole disrupts the binary and flips the spin axis before ejecting itself. That level of chaos is rare but possible in dense stellar environments. The detection proves it happens. By late 2025, the LIGO-Virgo-Kagra network has logged nearly 300 black hole mergers. GW24101 and GW24110 are among the most novel. They open a new category in black hole taxonomy. Not stellar mass, not supermassive, but second generation, formed from previous mergers, carrying the scars of their violent past in their spin and mass distributions. Number 2, black hole triples. 3 is not a crowd. 8,000 light years from Earth. Constellation Cygnus, V404. Cygni, known since 1938 when it flared as a nova, confirmed as a black hole in 1992, one of the first black holes ever verified. Over 1,300 scientific papers written about it. And nobody noticed the third star until April 2024. Kevin Burge at MIT is searching for new black holes using the Aladdin Light Sky Atlas. Out of curiosity, he reviews images of V404 Cygni, 2 blobs of light close together. The first blob is the black hole and its inner companion star, orbiting every 6.5 days. The companion sheds material onto the black hole, creating a bright accretion disk. Standard binary system. But the second blob is something different. Another star, much farther away, 3,500 astronomical units from the black hole. 1 AU is the Earth-Sun distance. This star is 3,500 times farther than that. The team uses data from the European Space Agency's Gaia survey to track stellar motions over 10 years. The 2 stars move together compared to background stars. They are gravitationally bound. Both orbit the black hole. V404, Cygni is not a binary. It is a triple. The first confirmed black hole triple system ever found. The outer star takes 70,000 years to complete one orbit. The inner star completes over 10 million orbits in the same time. The problem is physics. Black holes form from supernova. Massive stars explode. The core collapses into a black hole. The explosion releases energy equivalent to billions of suns. That energy kicks everything nearby. Any loosely bound companion star should be blown away. V404. Cygni's outer star is barely bound. The gravitational string holding it is like a spider web. Any strong tug should break it, yet it is still there. Burge runs thousands of computer simulations. Each starts with 3 stars. The third star evolves and dies. In supernova scenarios with varied explosion energies and directions, the outer star always gets kicked away. The system does not survive. But in direct collapse scenarios where the star simply caves in on itself without a dramatic flash, the outer star stays bound. The simulations match observations only when the black hole forms gently. No explosion, no kick, just collapse. Direct collapse has been theorized for decades but never confirmed. V404. Cygni provides the first direct observational evidence. The black hole weighs roughly 9 solar masses. It likely received a natal kick of less than 5 kilometers per second. For comparison, typical supernova kicks are hundreds of kilometers per second. This was barely a nudge. The star imploded quietly, and the outer companion never knew anything violent happened. The outer star is evolving. It is becoming a red giant. Using stellar evolution models, the team calculates the star is between 3 and 5 billion years old. Since all 3 stars likely formed together, the entire system, including the black hole, is the same age. The black hole has been quietly consuming the inner star for billions of years. It has eaten at least half a solar mass of material over that time. The feeding is slow, controlled, nothing dramatic. The discovery appears in Nature on October 23, 2024. The paper is titled The Black Hole Low-Mass X-Ray Binary Vi404 Cygni is part of a wide hierarchical triple and formed without a kick. Co-author Kareem El-Badri at Caltech confirms what the simulations show. Quote, "This system is super exciting for black hole evolution, and it also raises questions of whether there are more triples out there. End quote. If one well-studied black hole turns out to be a triple, how many others have we missed? Over 1,300 papers on V404 Cygni, and not one mentioned the third star until 2024. The implications reach beyond one system. If some black holes form through direct collapse, it changes formation models. It changes predictions for gravitational wave detections. It changes estimates of black hole populations in the galaxy. Supernovae are loud. Direct collapse is quiet. Quiet processes leave different signatures, different spins, different kicks, different binary survival rates. The entire framework needs adjustment. V404. Cygni sits in a hierarchical configuration, interbinary plus distant tertiary. This structure is predicted in evolutionary models of low-mass X-ray binaries, but observational confirmation was lacking. Now it is confirmed. The black hole actively feeds from the nearby star. The distant star orbits undisturbed. The system is stable and will remain stable for billions more years unless something external disrupts it. The black hole in V404. Cygni might not be alone in its formation mechanism. Other triples could be hiding in plain sight. Astronomers are now re-examining known binary systems with renewed scrutiny. Are there faint tertiary companions that were dismissed as background stars? Are there systems where the orbital dynamics hint at unseen third bodies? The search is on for it. Number 3. Primordial black holes, dark matter in disguise, January 2025. Yakov Zeldovich and Igor Novikov first proposed them in 1966. Stephen Hawking studied them in 1971. For over 50 years, they remained hypothetical. But recent work published in Physical Review D by Kazunori Kori at the National Astronomical Observatory of Japan proposes detecting them through gravitational waves induced by primordial curvature perturbations. The research was published in 2025 and provides the first concrete detection method for black holes that could make up dark matter. These are not your standard black holes. Primordial black holes form in the first fractions of a second after the Big Bang, not from dying stars, but from density fluctuations in the infant universe. Extremely dense pockets of subatomic matter collapse under their own gravity before the first stars even ignite. They can have masses ranging from asteroid size to stellar mass to potentially supermassive. No constraints from stellar evolution. No requirement for supernovae, just pure gravitational collapse in the early universe. If primordial black holes exist in sufficient numbers, they solve the dark matter problem. Dark matter makes up 85% of the matter in the universe, but nobody knows what it is. Candidates include weakly interacting massive particles called WIMPs and hypothetical particles called axions. But 50 years of searches have turned up nothing. Primordial black holes offer an alternative. They are non-baryonic, they exert gravity, they do not emit light. They fit every observational constraint for dark matter. The memory burden effect changes everything. Stephen Hawking showed in 1975 that black holes evaporate via quantum effects. The evaporation time scales with the cube of the initial mass. Only black holes heavier than about 10 to the 12 kilograms should have survived today. But if black holes carry information in a way that stabilizes them against evaporation, their lifetimes extend dramatically. Primordial black holes with masses below 10 million kilograms previously thought to have evaporated could still be present as cold dark matter today. Detection comes through gravitational waves. When primordial black holes form, they create ripples in space-time that persist. These induced gravitational waves from the primordial curvature, perturbations that created the black holes, carry a specific signature. Future detectors like the Laser Interferometer Space Antenna, scheduled to launch in 2035, could detect these waves. Kori's paper, published in Physical Review D on May 23, 2025, lays out the detection strategy. This is the first research proposing that evidence of primordial black holes being dark matter will be confirmed by future gravitational wave observations. Recent analyses from LIGO and Virgo hint at the possibility. Gravitational wave detections in March 2016 showed black holes merging with masses around 30 solar masses each. 3 independent research groups proposed these could be primordial. 2 groups found merging rates consistent with primordial black holes making up all dark matter if they cluster in halos like faint dwarf galaxies. The 3rd group argued the rates are too high in primordial. Black holes contribute less than 1% of dark matter. The debate continues, but the possibility remains open. Alexander Kashlinsky in May 2016 suggested spatial correlations in unresolved gamma-ray and X-ray background radiations could come from primordial black holes with similar masses if their abundance matches dark matter. In August 2019, a study opened the possibility of asteroid mass primordial black holes between 7 times 10 to the 13 and 8 times 10 to the 18 kilograms making up all dark matter. In September 2019, James Unwin and Jakob Schultz proposed a primordial black hole with 5 to 15 Earth masses, about the diameter of a tennis ball existing in the extended Kuiper belt, to explain orbital anomalies attributed to a hypothetical ninth planet. If primordial black holes formed in the early universe, they seed the supermassive black holes found in galaxy centers today. James Webb. Space telescope observations show supermassive black holes exist just 1.5 billion years after the Big Bang. There's not enough time for them to grow from stellar mass black holes through accretion. But if they started as primordial black holes with millions of solar masses, they have a head start. They grow quickly. They reach billions of solar masses by the time galaxies form. The puzzle of early supermassive black holes gets solved. The primordial black hole mass distribution is broad. Simulations suggest a mode around one solar mass with a wide spread. Many could have asteroid mass, but hydrogen atom size, traveling at enormous speeds. One likely passes through the solar system at any given time. Most would pass through stars like bullets without significant effects. The ones traveling slowly could get captured by stars. Stephen Hawking proposed the Sun may harbor such a primordial black hole inside its core. Charged primordial black holes are another twist. A paper published in October 2025 by Sebastian Schuster at Stockholm University titled Primordial Black Holes, Charge and Dark Matter, Rethinking Evaporation Limits, explores how charges present in the early universe remain preserved in primordial black holes even when corresponding particles disappear. Near-extremal charged black holes evaporate much more slowly than uncharged ones. This greatly extends their lifetimes and changes constraints on their contribution to dark matter. If primordial black holes are out there in large numbers, future surveys will find them. The next generation of gravitational wave detectors will be sensitive enough to detect the induced waves from their formation. Microlensing surveys will spot asteroid mass black holes passing in front of background stars. The mystery of the dark matter could finally be solved, not with exotic particles, but with black holes born at the dawn of time. Number 4. Rogue black holes, wanderers in the void, May 8, 2025, 600 million light years from Earth. Galaxy in a quiet corner of space. The Zwicky Transient Facility on the Samuel Oschin Telescope at Palomar Observatory detects a flare, designated AT2024TVD, optical wavelengths, bright, getting brighter. The position is unusual. Not at the galaxy center where supermassive black holes live, 2,600 light years offset from the core. Out in the galactic suburbs. Yuhan Yao at UC Berkeley leads the follow-up. Hubble Space Telescope images, taken January 16, 2025, pinpoint the location. Chandra X-ray Observatory confirms a tidal disruption event, a black hole tearing apart a star. The star drifted too close. The black hole's gravity stretches it like taffy. Spaghettification. The star shreds. Material spirals into the black hole. The process releases a burst of light that can outshine an entire galaxy for weeks. But this is the first tidal disruption event ever captured optically from a black hole far from a galaxy center. Roughly 100 TDEs have been observed since detection methods improved. All occurred at galactic cores. AT2024 TVD breaks the pattern. The black hole weighs roughly 1 million solar masses. Intermediate mass, not stellar, not supermassive, stuck in the middle, and it is a rogue, a wanderer. Displaced from where massive black holes are supposed to be, radio observations tell the rest. The Very Large Array in New Mexico tracks the event for 10 months. 2 distinct radio flares erupt 80 and 194 days after the initial optical detection. Delayed bursts, never seen before. Itai Sfaradi at UC Berkeley calls it extraordinary. Quote, "Never before have we seen such bright radio emission from a black hole tearing apart a star away from a galaxy's center and evolving this fast." End quote. The radio flares evolve faster than any TDE on record. Something about the off-nuclear environment or the black hole itself accelerates the emission. How did the black hole get there? 2 scenarios. First possibility. The black hole came from a small galaxy that merged with the larger galaxy billions of years ago. The smaller galaxy was consumed. Its core survived. The black hole now wanders through the larger galaxy on a slow orbit. Eventually it will fall to the center and merge with the central supermassive black hole, but that takes billions of years. Right now it is a rogue. Second possibility. The black hole was once part of a triple system at the galaxy center. 3 massive black holes orbiting in chaotic dynamics. 3-body problems are unstable. 1 black hole gets kicked out, the wanderer. The other 2 remain at the core. The kicked black hole travels through the galaxy, eating any stars that cross its path. Every 30,000 years on average, a star comes close enough for a tidal disruption event. AT2024 TVDs, it was one of those unlucky stars. Raffaele Margutti at UC Berkeley co-authors the study. Quote, "This is the first time that we actually see massive black holes being so close using TDEs." End quote. The discovery validates predictions. Theorists have long suspected wandering black holes exist, especially after galaxy mergers, but finding them is hard. They emit no light unless they feed. Tidal disruption events provide the smoking gun. Ryan Chornock at UC Berkeley adds context, quote, "These events hold great promise for illuminating the presence of massive black holes that we would otherwise not be able to detect." End quote. The discovery motivates theorists to compute rates for offset TDEs. Right now, models focus on central TDEs. Offset events have been ignored. That changes now. The ZATE-TF survey detects hundreds of optical flares every year. Most are at galaxy centers. Searching for offset events requires scanning the entire galaxy, not just the core. AT2224 TVD was found because it was bright and unusual. How many fainter offset TDEs are we missing? The Vera Rubin Observatory in Chile, set to begin operations, soon will survey the southern sky with the largest digital camera ever built. It will find more, many more. The rogue black hole in AT2024 TVD will eventually merge with the central black hole. The process could take billions of years. When it happens, it will produce gravitational waves detectable by the Laser Interferometer space antenna launching in 2035. The merger will be a test of general relativity in the intermediate mass regime. We do not have many observations of intermediate mass black hole mergers. This system is a preview of what LISA will see. Wandering black holes could be common. Every major galaxy has experienced mergers. Every merger brings in additional black holes. Some sink to the center quickly, others get stuck in wide orbits, others get kicked out entirely. The population of rogue black holes wandering through galaxies could number in the thousands per galaxy. We only see them when they eat. The rest remain invisible, but they are there, waiting, hungry. AT2024 TVD opens a new era. Systematic searches for offset tidal disruption events will reveal the hidden population. The universe has more wandering monsters than we thought. And everyone that we find rewrites our understanding of galaxy evolution, black hole dynamics, and the cosmic food chain. Number 5, intermediate mass black holes. The missing link? 17,700 light years from Earth? Omega Centauri, the largest and brightest globular cluster in the sky. Visible to the naked eye from southern latitudes, 10 million stars gravitationally bound in a sphere. Listed as a single star in Ptolemy's catalog nearly 2,000 years ago, Edmund Halley reported it as a nebula in 1677. John Herschel recognized it as a globular cluster in the 1830s. But Omega Centauri is different from other globular clusters. It rotates faster. Its shape is flattened. It is 10 times more massive than typical globular clusters, almost as massive as a small galaxy. Characteristics that suggest it might be the core of a dwarf galaxy that was swallowed by the Milky Way billions of years ago, stripped of its outer stars, the nucleus frozen in time. Maximilian Haberle at the Max Planck Institute for Astronomy leads a team that analyzes over 500 Hubble Space Telescope images spanning 2 decades. They create a catalog measuring velocities for 1.4 million stars. Most of these Hubble observations were for instrument calibration, not science, but they turn out to be ideal for studying stellar motions. The catalog is the largest ever for any star cluster. In the innermost 3 arc-seconds of the cluster, 7 stars move extraordinarily fast. Their velocities exceed the escape velocity. They should leave the cluster and never return, but they do not. Something massive is holding them. The only object that can exert that much gravitational pull is a black hole. The team calculates a firm lower limit of 8,200 solar masses. That mass puts the black hole squarely in the intermediate mass category. Intermediate mass black holes are rare. Stellar mass black holes form from dying stars with masses under 100 solar masses. Supermassive black holes at galaxy centers have masses from millions to billions of solar masses. The gap between 100 and 1 million solar masses is the missing link. Intermediate mass black holes should exist as evolutionary steps from stellar to supermassive, but finding them is notoriously difficult. Several studies had suggested an intermediate mass black hole in Omega Centauri, but other studies proposed the mass could come from a cluster of stellar mass black holes at the center. The lack of fast-moving stars above escape velocity made the intermediate mass black hole hypothesis less convincing. Until now, the discovery of 7 fast stars changes everything. Nadine Neumeier at Max Planck co-leads the study. Quote, "This is the most direct evidence so far of an intermediate mass black hole in Omega Centauri. This is exciting, because there are only very few other black holes known with a similar mass. The black hole in Omega Centauri may be the best example of an intermediate mass black hole in our cosmic neighborhood." End quote. If confirmed, the black hole is closer to Earth than Sagittarius A star, the 4.3 million solar mass black hole at the center of the Milky Way, located 26,000 light-years away. Anil Seth at the University of Utah calls it a once-in-a-career finding. Quote, "I've been excited about it for 9 straight months. Every time I think about it, I have a hard time sleeping. I think that extraordinary claims require extraordinary evidence. This is really, truly extraordinary evidence." End quote. The detection resolves a decade-long debate. Omega Centauri harbors a central black hole. The missing link exists. The black hole formed billions of years ago when Omega Centauri was the core of a separate dwarf galaxy. That galaxy merged with the Milky Way. The outer stars were stripped away. The core remained intact. The black hole at the center stopped growing. No more gas to accrete, no more stars to merge with. It is frozen at intermediate mass, a relic of an earlier phase of galaxy evolution. Intermediate mass black holes answer critical questions. How do supermassive black holes grow? Current models struggle to explain how black holes reach billions of solar masses in the time available. If they start as intermediate mass black holes, they have a head start. They grow through accretion and mergers. They reach supermassive status faster. Omega Centauri's black hole provides observational proof that intermediate mass black holes exist and can be the seeds of larger black holes. The discovery was published in Nature on July 10, 2024. The paper is titled "Fast-Moving Stars Around an Intermediate Mass Black Hole in Omega Centauri." Co-authors include astronomers from institutions in Germany, the United States, and several other countries. The catalog of stellar velocities will be made openly available for future research. Beyond Omega Centauri, other intermediate mass black hole candidates are emerging. The Dark Energy Spectroscopic Instrument discovered the largest sample ever of intermediate mass black holes and dwarf galaxies hosting active black holes in February 2025. Within DESI's early data, scientists uncovered 300 new intermediate mass black holes, plus 2,500 new active black holes in dwarf galaxies. The population of missing links is larger than expected. Intermediate mass black holes could produce tidal disruption events similar to AT 2024 TVD. They could merge with other intermediate mass black holes, producing gravitational waves in a specific frequency range. They could exist in dense star clusters waiting to be found. Omega Centauri shows us they are real. The search for the missing link is over. Now the hunt is on for more. If you've been following along, you know we're halfway through the weirdest black holes in the universe. Subscribe now so you don't miss the rest. Comment from which city you're watching, and let us know which type of black hole surprised you the most so far. Back to the discoveries. Number 6, Porphyrion, the jet that crosses the cosmic web. 7.5 billion light-years from Earth, constellation Boats, 23 million light-years of plasma shooting through space, 140 Milky Way galaxies laid end to end. That is the length of the largest black hole jets ever observed, nicknamed Porphyrion after a giant in Greek mythology. Discovered in September 2024 by Martijn Ooy at Caltech using Europe's low-frequency array radio telescope. Published in Nature on September 18, 2024. The jet pair launches from a supermassive black hole at the center of a massive galaxy. The galaxy weighs about 10 times the mass of the Milky Way. The black hole is feeding. Material spirals into an accretion disk. Magnetic fields twist and tangle. Some material gets funneled into 2 opposing jets shooting out above and below the black hole at nearly the speed of light. The jets blast through intergalactic space for billions of years, unperturbed, almost perfectly straight, heating surrounding gas by 1 million degrees Celsius, carrying the power equivalent of trillions of suns. Before Porphyrion, the record holder was Alcyonius, discovered in 2022 by the same team. Alcyonius spans 16 million light-years, or 100 Milky Ways. The well-known Centaurus. A-jets, the closest major jet system to Earth, span 10 Milky Ways. Porphyrion beats Alcyonius by 7 million light-years. It is 40% larger and was previously thought to represent a theoretical maximum. Porphyrion dates to when the universe was 6.3 billion years old, less than half its current age of 13.8 billion years. At that epoch, the cosmic web was denser. The wispy filaments connecting galaxies were closer together. Jets like Porphyrion reached across a greater portion of the cosmic web than jets in the local universe. The team calculates Porphyrion's jets could span 2/3 of the way across voids between cosmic filaments. That means every place in the universe may have been affected by black hole activity at some point in cosmic time. The discovery comes from a sky survey using LOFAR. The survey was searching for filaments of the cosmic web. Instead, it found over 10,000 massive jet systems spanning roughly 3 million light-years or more. Porphyrion is the largest, but it is not alone. Martin Hardcastle at the University of Hertfordshire leads the survey. Quote, "Giant jets were known before we started the campaign, but we had no idea that there would turn out to be so many." End quote. The sheer number is surprising. Giant jets are not rare anomalies. They are common features of the distant universe. Follow-up observations use the Giant Microwave Radio Telescope in India and the W.M. Keck Observatory in Hawaii. Keck's low-resolution imaging spectrometer reveals that Porphyrion emerged from a radiative mode active black hole. Radiative mode black holes were not thought to produce large jets. They are too busy radiating energy from infalling gas. Jet mode black holes with less radiation are supposed to make the big jets. Porphyrion proves that assumption wrong. Radiative mode black holes can produce colossal jets if conditions are right. The jets influence galaxy formation. Galaxies form from collapsing gas. If the gas is too hot, it does not collapse. Black hole jets heat intergalactic gas. Porphyrion's jets heat surrounding space by 1 million degrees. That heat can slow or prevent galaxy formation. In the early universe, when Porphyrion was active, the cosmic web was denser. The jets reached more galaxies. The impact on galaxy formation was greater than in the present universe. George Georgovsky at Caltech provides context. Quote, "Astronomers believe that galaxies and their central black holes co-evolve. And one key aspect of this is that jets can spread huge amounts of energy that affect the growth of their host galaxies and other galaxies near them. This discovery shows that their effects can extend much farther out than we thought." End quote. Black hole jets are not just galaxy-scale phenomena, they are cosmic-scale phenomena. They shape the large-scale structure of the universe. How the jets stay straight across 23 million light-years is a mystery. Jets can bend if they hit a dense cloud or if the black hole changes orientation or if strong magnetic fields push them. Porphyrion has none of those issues. It has been blasting for roughly 2 billion years unperturbed. That level of stability requires an unusually long-lived and stable accretion event around the black hole. The black hole needs to keep feeding at a steady rate for 1 billion years, and the jets need to keep pointing in the same direction the entire time. The mechanics of maintaining that stability are not fully understood. Porphyrion could affect Earth's magnetic field indirectly. Earth's magnetic field connects to the Sun's magnetic field. The Sun's magnetic field connects to the Milky Way's magnetic field. The Milky Way's magnetic field could connect to larger-scale magnetic fields stretching across the cosmic web. If structures like Porphyrion magnetized intergalactic space billions of years ago, those magnetic fields could still influence our local environment today. The connection is long and tenuous, but it traces all the way back through time and space to jets like Porphyrion. The LOFAR survey continues. More giant jets are being discovered. The population of jet systems spanning millions of light years is larger than anyone expected. As radio telescope technology improves, even larger jets may be found. Porphyrion might not hold the record forever, but for now, it is the king. The largest black hole jet system ever observed. A monument to the power of supermassive black holes, and a reminder that the universe operates on scales far beyond human intuition. Number 7, Lid 568, the Super Eddington black hole. 1.5 billion years after the Big Bang. A black hole defies the laws of physics. It is eating 40 times faster than it should. The theoretical feeding limit, called the Eddington limit, is the maximum rate at which a black hole can accrete matter before radiation pressure pushes material away. LID 568 ignores that limit. It feeds at 40 times the Eddington rate. And it keeps growing. The discovery comes from the James Webb Space Telescope and the Chandra X-ray Observatory. An international team led by Hyewon Soo at the International Gemini Observatory analyzes a sample of galaxies from Chandra's Cosmos Legacy Survey. These galaxies are extremely bright in X-rays, but invisible in optical and near-infrared wavelengths. JWST's unique infrared sensitivity detects faint counterpart emissions. LID 568 stands out. Intense X-ray emission. Exact position unclear from X-ray data alone. JWST pins it down. The black hole weighs between 17 billion and 19 billion solar masses. It powers the brightest quasar ever seen by humanity. Maintaining this emission requires consuming the equivalent of the sun's mass in gas and dust every single day. 1 solar mass per day. For comparison, Sagittarius A star at the center of the Milky Way accretes a tiny fraction of a solar mass per year. LID 568 is a glutton. Super Eddington accretion explains how supermassive black holes grew so quickly in the early universe. JWST observations show supermassive black holes existed just a few hundred million years after the Big Bang. There is not enough time for them to grow from stellar mass seeds through standard accretion. But if they undergo short periods of super Eddington feeding, they can grow rapidly. LID 568 provides direct evidence. The feast is short-lived. The black hole will eventually exhaust nearby gas, or radiation pressure will shut off accretion. But during the feeding frenzy, it gains mass at an incredible rate. The discovery was announced in February 2024. The paper was published in November 2024. The findings help explain why so many giant black holes appear so early in cosmic history. If super Eddington accretion is common in the early universe, then black holes can reach billions of solar masses in under 1 billion years. The growth problem is solved. Theorists also proposed how black holes seeded the universe without emerging from dead stars. Rapidly collapsing pockets of gas formed primordial black holes in the early universe. Most of these singularities evaporated via Hawking radiation, but the ones that survived gorged and merged at a breakneck pace. Super Eddington feeding accelerated their growth. They reached supermassive scales quickly. LID 568 fits this scenario. It could be one of those primordial black holes now revealed in its feeding frenzy. The Eddington limit assumes spherical accretion, but if accretion is not spherical, the limit changes. Disk accretion with strong magnetic fields can channel material directly onto the black hole by passing radiation pressure. LID 568 might have a thick accretion disk, or a warped geometry that allows super Eddington rates. The exact mechanism is still debated, but the observation is clear. The black hole is eating faster than theory allows. LID 568 is located 12 billion light-years away. We see it as it was 12 billion years ago. The light has traveled across most of the universe to reach us. The black hole today, if it still exists, could be much larger. It could have merged with other black holes. It could be at the center of a massive galaxy. Or it could have exhausted its fuel and gone dormant. We will never know because we can only see its past. The discovery challenges black hole formation models. Standard models assume Eddington-limited accretion. LID 568 shows that assumption is too conservative. Black holes can exceed the limit, they can grow faster, they can reach larger masses in shorter times. Every assumption in black hole physics needs re-examination. The universe is weirder than the textbooks say. Black holes come in flavors we are just beginning to catalog. Second-generation black holes form from earlier mergers spinning at cosmic speed limits. Black hole triples with distant companions, proving gentle formation without supernovae. Primordial black holes from the Big Bang possibly making up dark matter. Rogue black holes wandering galaxies, tearing apart unlucky stars. Intermediate mass black holes bridging the gap between stellar and supermassive. Porphyrion shooting jets across 23 million light-years heating the cosmic web. LID 568 eating 40 times faster than physics allows. 7 types. 7 puzzles. And every single discovery came in the last 2 years. LIGO and Virgo detecting gravitational waves with unprecedented precision. Hubble analyzing stellar motions across decades. JWST peering into the early universe with infrared eyes. Chandra mapping X-ray emissions from feeding black holes. LOFAR scanning radio frequencies for giant jets. Keck measuring spectra of distant galaxies. The tools are better. The data is richer. The discoveries are accelerating. What comes next? More detections? More anomalies? More types that do not fit the categories. The taxonomy of black holes is incomplete. Every new instrument reveals phenomena that were predicted to be impossible. Black holes spinning backward, black holes in triples, black holes forming without explosions, black holes older than galaxies, black holes with jets longer than galaxy clusters. The universe does not care about our models. It does what it wants. And the more we look, the more we find that our textbooks are wrong. Black holes are not just dark monsters swallowing light. They are sculptors of galaxies. They are relics of the Big Bang. They are wanderers through cosmic voids. They are missing links in evolution. They are jets that cross the cosmic web. They are feeders that ignore physical limits. These are the 7 weirdest types of black hole we know about so far. But the universe is large. 14 billion years old, 93 billion light-years across, full of places we have never looked. Full of phenomena we have never imagined. The weird black holes we found are probably the tip of the iceberg. The really strange ones are still out there, waiting, hidden in the data, lurking in the dark, until the next observation campaign. Until the next gravitational wave detection, until the next survey image that shows something nobody expected. The search continues. The universe keeps its secrets close. But piece by piece, year by year, detection by detection, we are learning what it hides. And every discovery makes one thing clear. The universe is stranger than we ever thought possible, and black holes are the strangest things in it.